Welcome, everyone. Today, we are tackling a critical data engineering capability, integrating Apache Hive with Apache Spark. Let's dive in and elevate your big data architecture skills. Let's start by defining what Hive and Spark integration actually is. At its core, it is the bridge between Spark's lightning-fast in-memory processing engine and Hive's centralized metadata catalog, known as the Hive Metastore. As you can see in the first bullet, this integration allows your Spark applications to natively read, write, and manipulate Hive tables using Spark SQL. Why does this matter? Because the Hive Metastore acts as your organization's single source of truth for schemas, data types, and file locations. When Spark connects to Hive, it doesn't use Hive's traditional, slower MapReduce or TES execution engines. Instead, Spark leverages its own Catalyst optimizer to execute the SQL queries with incredible speed. You get the best of both worlds, Hive's structural governance and Spark's computational power. Looking at this flowchart, you can see the architecture at a high level. On the left, Apache Spark SQL sends a metadata request to the Hive Metastore. The Metastore replies with the schema and the exact location of the data on the storage layer. Spark then bypasses the Metastore to directly read and write the underlying Parquet or ORC files in your data lake, such as HDFS or Amazon S3. It's a highly efficient decoupling of metadata and data. Now that we know what it is, why should you implement this integration? The primary reason is to establish a shared data catalog. Without integration, Spark developers might define schemas in their code, creating isolated data silos. By integrating with Hive, you centralize your schema management. Furthermore, this enables true ecosystem interoperability. A data engineer can clean and aggregate terabytes of data using Spark, save it to a Hive table, and immediately, a business analyst can query that exact same table using BI tools like Tableau via Hive Server 2. Additionally, managing schema evolution becomes seamless. If a column is added in Hive, Spark recognizes it instantly. Finally, it unlocks advanced analytics by allowing you to pipe structured, governed warehouse data directly into Spark's machine learning libraries. This mind map breaks down the core benefits. At the center is our primary goal, integration. Branching out, we see the shared catalog guaranteeing a single source of truth. Moving clockwise, interoperability bridges the gap between Spark's processing and external BI tools or engines like Impala. Down below, we highlight schema evolution for centralized updates and finally, the seamless access it grants to Spark mlib for advanced predictive modeling. Let's move from the why to the how. How do we actually configure this integration? At the infrastructure level, Spark needs to know where your Hive Metastore lives and how to communicate securely with your cluster. You achieve this by copying your cluster's hivesite.xml, coresite.xml, and hdfsite.xml files directly into Spark's conf/directory. These files contain critical properties, such as the Metastore Thrift URI and Kerberos security credentials. As noted in the second bullet, it's crucial that both your Spark driver and all worker executors have unrestricted network access to that Metastore URI. Finally, ensure your Spark distribution is built with Hive support. In rare cases involving legacy systems, you may also need to explicitly declare the Hive version in your Spark configurations to ensure compatibility. This diagram illustrates the configuration flow. On the left, we inject the XML configuration files into the Spark conf directory. These settings propagate to both the Spark driver and the Spark executors. Armed with this configuration, both the driver and the worker nodes can successfully negotiate a connection over the Thrift protocol, typically on port 9083, directly to the central Hive Metastore. With the infrastructure configured, let's look at the code. In Spark 2.x and 3.x, the Spark session is your primary entry point. To activate the integration programmatically, you simply append the method .enable Hive support when building your Spark session object. This single line of code instructs Spark to look for the hivesite.xml and connect to the Metastore. Once connected, your programming capabilities expand dramatically. You can use Spark.SQL to write native HiveQL queries including executing DDL statements like create table or drop table. Alternatively, if you prefer the DataFrame API, you can use Spark.table, passing the Hive table name, which instantly loads the Hive data into a distributed Spark data frame, ready for complex transformations. Let's walk through this sequence diagram. The developer initiates the Spark session using Enable Hive support. Spark reads the XML configs and handshakes with the Hive Metastore. Once established, the The developer submits a SQL query. Spark transparently asks the metastore for the table's schema and file path. The metastore returns these details, and Spark physically executes the read, returning a populated data frame to the developer. Let's deep dive into how Spark interacts with different Hive table types. It's critical to understand the distinction between external and managed tables. With external tables, Hive only manages the schema. The data sits safely in your data lake, and dropping the table leaves your files intact. Spark handles external tables natively and exceptionally well. Managed tables, however, are strictly owned by Hive. If you drop a managed table, the underlying data is deleted. When writing data frames back to Hive, pay close attention to your storage format. ORC-optimized row columnar is the gold standard for Hive performance. To get the absolute best performance, ensure you enable Spark's native vectorized ORC reader in your configurations, which processes data in columnar batches rather than row by row. This class diagram emphasizes the inheritance and behavioral differences of Hive tables. Both inherit the base properties of a table name and schema. However, the external table explicitly points to an external location and protects data upon dropping. Conversely, the managed table defaults to the internal Hive warehouse directory and destructively deletes both metadata and data when the drop command is executed. As enterprise architectures upgraded to Hive 3, a new challenge emerged. Hive 3 introduced ACID transactional managed tables, which native Spark cannot read directly due to complex Delta files and compaction logic. The solution is the Hive Warehouse Connector, or HWC. HWC is a specialized library that bridges this gap. It offers two primary read modes. First is the direct reader mode, where Spark securely accesses the Hive metastore to get the transaction snapshot, then reads the data directly from the file system, ideal for high-speed, heavy ETL jobs. The second is JDBC mode. Here, Spark routes the read request through Hive Server 2. While slightly slower, it enforces Apache Ranger's fine-grained access controls, like row-level filtering and dynamic column masking. This flowchart demystifies the Hive Warehouse Connector's routing logic. The Spark job invokes HWC, which evaluates the configured read mode. If configured for direct reader, it bypasses the compute layer and grabs the data straight from HDFS using the ACID snapshot. If JDBC mode is selected, the request is forced through Hive Server 2, which intercepts the query to enforce Apache Ranger security policies before ultimately serving the data back to Spark. Let's cement this with a highly impactful real-world use case, a centralized ETL pipeline for a major retail company. Imagine we need to merge high-velocity streaming web logs with slow-moving legacy CRM data. First, we use Spark structured streaming to ingest the JSON logs from Apache Kafka. Within the same Spark application, we transform, cleanse, and join this streaming data with our CRM dimensions. Here is where the integration shines. We take that enriched Spark data frame and write it directly to a partitioned Hive external table using the Parquet format. The outcome: we have established a single source of truth. Data scientists can instantly attach their Jupyter notebooks via Spark to train recommendation models, while business analysts can currently fire up Tableau, connecting via Hive Server 2, to build executive dashboards on the exact same dataset. In this pipeline diagram, raw inputs from Kafka and our CRM system feed into our central Spark ETL job. Spark does the heavy lifting and writes the output directly into our centralized Hive ecosystem. From there, the data diverges securely to multiple consumers, business intelligence tools via Hive Server 2 on the right, and programmatic data science workflows via Spark mlib on the left. To wrap up, let's look at best practices. Always partition your Hive tables logically, such as by date or region, which allows Spark's predicate pushdown to skip irrelevant data, drastically reducing I/O. Be vigilant about the small files problem. Always use Spark's coalesce or repartition methods before writing to Hive to ensure you generate optimally sized files. If your industry requires strict regulatory compliance, absolutely utilize the Hive Warehouse Connector in JDBC mode to leverage Apache Ranger security. In summary, integrating Spark with Hive provides the ultimate combination of distributed computational scale and robust enterprise governance. Thank you for joining this deep dive. Please like, subscribe, and visit quicktechie.com for premium certification prep, including Q&A banks, full ebooks, audiobooks, full-length training, and comprehensive interview guides to accelerate your career. This final diagram synthesizes our best practices. Smart partitioning, careful management of output file sizes, and enforcing robust security policies all converge into a single, highly optimized Spark and Hive pipeline. Applying these principles ensures your big data architecture remains scalable, performant, and secure for years to come.